some books, name of the books for the I should say that the theoretical part, that is the mathematics behind the numerical methods. For that, you have Numerical Engineering Computation. That is the name of the book. It is by Jane Iyengar Jain. So I'll just write it in the chat box, so you can get it from there.
If you have a soft copy, then please send us.
I do not have a soft copy of this, unfortunately. So this one is Jane. Yes.
So roll number 38 is present.
Okay. Be there. At the end of the class, do remind me again. I will just change it. Okay.
Okay, sir.
So the first book, that is mainly the theoretical part of it. That means the mathematics behind the various numerical methods that we would be covering is given in this book, Numerical Methods. It's just a short abbreviation of the full name. The full name is Numerical Methods for Scientific and Engineering Computations by Jane Iyengar Jain. It's a good book. You can follow that. And for the computer implementation part, I'm going to recommend a book, Computer-Oriented Numerical Methods. This one is by Rajaraman, B. Rajaraman. Excellent book. Hardly around 200 pages. It's a very small book, and in very precise and concise manner, different algorithms that we will be covering for various numerical methods are explained over in this book. So for the computer implementation part, you can refer to this computer-oriented numerical methods. It's not expensive also, available in Amazon as well as Flipkart. Around with, I think, discounts and all, you will get it well around 200 rupees. So that would be all. And what is it you are sharing over here?
Just soft copy it. Soft copy it.
Do not share it. Konta prothom ekta.
Prothom ekta sir.
But I would just request you not to share the PDF copies in the official class. Okay, this is an official class. Do not share the electronic copies in while the class is going on. You are, of course, free to share it with your friends over in your, if you have a WhatsApp group. That's absolutely fine, no problems. But not in the official class. Usually, it has got something to do with the piracy and all that. Means this is a available book, so the authors would be expecting to receive some kind of monetary rewards from their effort in writing the book. So don't just do it in the official forum. Obviously, you can share it with your friends, but not here. Okay. Is that understood? I'm not telling you not to share, but just don't do it in this platform. Is that okay?
Yes, sir. Yes, sir.
Okay. So that's all regarding books. There are also lots of other books available. So one very good book is, again, I do not recall the exact name. It's Numerical Methods for Engineers or something like that, along that line. It's by Chapra and Kanale. That is also a very good book that you can follow. Okay, so now let us start our proper class. I'll first of all share the screen. Tell me if you can see it.
Yes, sir, visible.
Okay.
Sure.
And I'll need to start recording as well. Once it starts, I'll switch over to the presentation. can see the presentation, right?
Yes, sir.
Yes.
Okay. Okay. So good morning to all of you, and welcome to the second class of the course, Numerical Analysis. The topic of discussion for today's class is errors associated with numerical analysis. But let us start today's class with this beautiful picture. Photograph of a sunset at St. Mary Lake in Montana, USA. What this has got to do with errors, you might ask. I will explain, obviously, and let me explain. It's a bit of a long explanation, but an interesting one. I hope you find it interesting as well. By the way, indeed, this is a very beautiful photograph, something that you would want maybe as a wallpaper for your desktop, or even as the background of your smartphone. And people indeed used it in such a way that they cropped it out from the original photo, and it was applied to smartphones as wallpaper. But there was a problem. In fact, a big problem. It crashed the phones. Not all phones, by the way. Only Android phones, specifically those running on Android 10, had this kind of a problem. It sent the phones in an infinite cycle of restarts, known as boot loop. This is specifically a state when the device tries to boot or start up, but fails as it encounters a problem. And what happens then? It tries to restart the booting process again. It encounters the problem again, reboots again. So it happens repeatedly. And that is what happened with Samsung phones and Google phones running on Android 10. People suffered this problem, but the only way out was to go for a factory reset in safe mode. That means all the data on the phone is completely lost as it is wiped clean. So what was the problem? Usually the first suspect is virus or malware. And people thought that this was the case here as well, that it was designed in such a way so as to cause the phones to crash. But after investigation, it came out that it is definitely not so. It was not a virus or a malware. The problem... Yes, go ahead.
স্যার এটা কালার পিক্সেলের জন্য হয় না?
I'll come to that. I'll explain. It has to do with color. The problem lies with the color space conversion, and in fact, luminance of a single pixel. Now, there are quite a few things to look at here. First of all, let me explain about color space, then we'll come to luminance and pixels. Take a look at this diagram. This diagram over here represents the visible color space. This one, this big one, colorful area that you see, that represents all the colors that a human eye can perceive. So this is the visible color space. The small triangle inside it, the yellow triangle over here, is the sRGB color space. Obviously, it's a subset of the full visible range. And the Android phones are run on this sRGB color space. That means these are the colors that the Android phones understand. Now, this is done in order to maintain consistency with all other devices, because most of the electronic devices, including printers, scanners, and all those things, they run on, obviously, the desktop backgrounds as well, desktop visual modules as well. They run on sRGB. So to maintain consistency, Android phones also run on sRGB. But obviously, there are other color spaces as well. For example, you can see here this blue triangle that represents the Adobe RGB. And this big red triangle over here represents the ProPhoto RGB. And this is the color space in which the original photograph in question was encoded. Now, advantage of this is that because it's a wider color space, it makes the photos look more vibrant. Quite obvious, it deals with an ultra-wide color space. However, it is not that the Androids can't handle this kind of a color space. That means ProPhoto RGB. They have the capability to convert a ProPhoto image into sRGB. The conversion module is available. And by conversion, we mean that if suppose a point is somewhere around here, for example. So once this conversion is done, this point obviously would move over to here in the sRGB color space. So that is what we mean by the conversion of color space. And as I said, Androids also have the capability of handling ProPhoto RGB. However, this conversion, the original image being in ProPhoto RGB and the Android phone color space being sRGB, so there has to be a conversion in between, and this conversion was the source of the problem. Android could not successfully convert the image. There was problem with a single pixel. The Google color engine, for the life of it, could not convert one particular pixel somewhere in this golden region of this photograph, somewhere around here. That particular pixel created the problem. To be more specific, the problem was with the luminance of a single pixel. Now, we all know that the screen, any electronic screen, is basically a matrix of pixels. Each pixel capable of a certain range of colors. And that is how we see images on screen. Now, what is luminance? Luminance is basically brightness, adjusted for the way humans see it, see different colors. You may know this, that humans see green tones far better than the red tones, and we see reds even better than blue. So the luminance of a pixel is calculated in case of Androids by this following formula. You can see that this is a weighted average where the most weight is given for the green. You can see it here. That this has the most weightage, red has the next highest weightage, and blue has the minimum weightage. And that is equivalent to the way we perceive different colors. So you need just a little bit of green to equivalently show a lot of the blue color. So the luminance of a pixel is calculated by this formula. The maximum value of R, G, or B individually is 255. So that is the maximum value for each of these parameters. And as this is a weighted average, the maximum value of the luminance of a pixel becomes 255 as well. The formula is, as I said, basically a weighted average. So it is only possible to get a maximum value of 255 from it. Now, the pixel that created the problem, let us just refer to it as the faulty pixel. That pixel has incredibly high R, G, and B values. R was 255, G was 255, and B was 243. So if you plug this in the formula, you get a value of 254.1336. So this is less than 255, no problems there. The problem arises when Google uses a form of rounding. That is, we are trying to represent a particular number with some other number because it's a case of representation. There is a fractional value over there, and we are rounding up to some integer value. Because of this rounding, now 54 was converted to 55, 182 goes to 183, and 17 goes to 18. That is the rounding up. If you add these together, you get a value of 256, which is obviously more than 255, and that is the error. So Android did not know how to handle this exception. This is an exception. It is a value which is out of bounds. So what did it do? It went for the only response available to it, that is reboot. But you have already applied this wallpaper as this image as the wallpaper. So obviously it has to process the wallpaper when it boots up. Now encountered the same problem again. And as a result, it went into an infinite loop of boots and reboots and restarts. So this simple error, very simple error. What is at the heart of the error? The rounding up. Finite representation of some numbers. And because of that, we had this kind of a problem. So I hope this has been an interesting explanation. And I hope that this also serves as the basis for today's lecture in trying to understand what errors are, how we can quantify them, and how we can minimize such errors. This is, by the way, is known as a kind of error in numerical analysis as round of errors. And we'll obviously look at round of errors in the course of our discussion. By the way, you have already done the computer programming course. Can you suggest a very simple remedy for this error? It's not difficult. Can you think of a programming remedy for such kind of a situation? It will probably be 2 or 3 lines.
স্যার এরকম তো হতে পারে ধরুন 5 বা 7 বার বুট হওয়ার পরে আবার সেই প্রিভিয়াসটাই চলে এলো, মানে যদি হলো ঠিক আছে, না হলে আবার প্রিভিয়াসটাই চলে এলো, প্রিভিয়াস যে
ওই ইন্টিজারের জায়গায় ফ্র্যাকশন ইউজ করব।
Yes, if you do that, that is also acceptable. Fine, no problems with that. But
if else statement where we can set the maximum limit to 255 in all other cases.
That is absolutely correct. If I have this luminance value, let's say LP, luminance of a pixel, which becomes greater than 255, we will set LP as equal to 255. So that is the simple bit of code that could have avoided this problem. And obviously, it has been rectified from the next version of Android onwards. So from Android 11 onwards, you do not have this kind of a problem. So let us now move forward and have a look at the topic of errors in a more formal manner. We have already defined numerical analysis as a problem-solving tool in the domain of mathematics in our previous class. So this is the definition that was given. It was also emphasized that it provides approximate solutions to complex engineering problems. As soon as you mention the word or phrase approximate solution, it means that the results provided by the numerical methods are not exact. There is, in fact, a gap between the exact or true value and the answer given by the numerical procedure. This gap is what is known as the error. Any solution obtained through numerical analysis, let's call it a numerical solution, is associated with errors. So all numerical methods and solutions provided by these methods are inherently linked with errors. Of course, the amount of the error, that is its magnitude, varies depending on a lot of factors. And one needs to scrutinize a numerical solution very closely so as to find out whether the solution is suitable or not, whether it is suitable for the purpose, for the application or not. Obviously, a solution having a large amount of errors is definitely not acceptable. But on the other hand, if the error is small enough, then probably that can be accepted. That raises the question that how big is too big? Or for that matter, how small an error is acceptable? These are valid questions. And the answer often depends on the type of the problem or the nature of the application where it is going to be applied, the solution is going to be applied. But it also points to the requirement of quantifying errors. Overall, one needs to be able to identify, quantify, analyze, interpret, and finally reduce errors in order to effectively use numerical methods as a problem-solving tool. And in order to deal with the issue of errors, certain factors need to be considered. These factors being, first of all, the origin of error. That means you need to identify the source of error, where this error is coming from. Secondly, quantification of error. That means putting a value to this error, numerical value, of course. And the third is minimization of error. That means you want to reduce the error as per requirement. Bring the level of error down to an acceptable limit. So these are the factors that one has to deal with. And of course, we'll start with the origin of errors. This is where we identify the source where the error is coming from. And obviously, these errors can rise from various different factors. These different types of errors, that means errors arising out of different sources that are associated with the numerical analysis, always limit the accuracy of the numerical solutions. So they have the same effect. Although they are arising from different sources, different origins, they have the same effect on the solution. They put that solution away from the accurate value, the exact value. So it limits the accuracy of the numerical solutions. We can identify three major sources of errors in the context of obtaining solutions through numerical analysis. The first one is human error. And this type of errors can also be categorized further. What are these subcategories? First one is a modeling error. That is, the mathematical model that you have proposed for the physical problem has some errors in it. Most of the cases, these errors arise out of wrong assumptions. You have made certain simplifying assumptions about the physical model in order to convert it to a mathematical model. If those assumptions are not correct, if those assumptions are not valid, if they are unacceptable, then of course the mathematical model that you have built upon those assumptions is going to provide you with erroneous results. In the last class, we have talked about an example of airdropping certain relief material in a flood affected zone with the help of a parachute. This physical problem was converted to a very simple mathematical model where we considered the drag or air resistance as proportional to the velocity. Suppose that assumption is wrong. Instead of this linear dependency, the drag force or the air resistance actually depends on the square of the velocity. So if that is the actual case, and in your mathematical model, you have considered the drag force to be proportional to velocity only, that is a linear function you have considered, then obviously your mathematical model is wrong and the result you will be getting from it. Even if you have solved the problem correctly, you have used the appropriate numerical methods and obtained a result with sufficiently less amount of numerical errors, then also it will give you an erroneous result because your mathematical model itself is wrong. So that is the kind of error that we characterize under modeling error. Next, we have logical error. These may occur in the logic of solving the problem. That is, the algorithm that you have developed for obtaining the solution has got certain errors in it. It does not truly replicate the numerical method that you are trying to create. So that kind of an error is known as a logical error. There could be arithmetic or programming errors as well. So these are basically best understood by, let's say, talking about the rules and regulations of the programming language itself. You have already written certain programming or programs or codes in your previous semester course of C programming, computer programming. And there you have seen that if you have gone wrong with the syntax of the language, you obviously get errors. And in some of those cases, you obviously do not get a solution as well. You get error messages. So mistakes in rules about priority and orders of operation results in arithmetic errors. And the problems in syntax of the programming language results in programming errors. If you do not follow the precedence of the different operations in C, you will obviously get erroneous results. On the other hand, if you do not follow the syntax of C, you will also get programming errors. So these are the causes of arithmetic and programming errors. Finally, there is also input errors. That means errors due to wrong input of data. A particular type of data is required as the input, but what you have supplied is not that type of data. So that can also create an error which is known as the input error. Now, how do we avoid these sort of human errors? It is very difficult to avoid human errors. Only thing that can be said against it is that you have to be very, very careful. But although if you are very careful, then also it is not possible sometimes to avoid certain of those human errors. So the point here that is to be made is that these are not systematic, and these cannot be systematically minimized. So there lies the problem. Not only that, such errors could be very hard to detect as well. Only when the numerical procedure gives an obviously incorrect solution or result, then you can probably get to understand that there is something wrong with the process. And if it is due to human errors, then it is very difficult to detect. And due to this reason, we will not consider these sort of errors in the purview of the present course that we are going to pursue. In the present course, we are only going to look at two different types of errors which are systematic: truncation error and round-off. Truncation error happens due to truncation of a mathematical procedure, whereas the round-off error occurs when you truncate the mathematical number, mathematical entity, you can say. So these errors occur due to different reasons. Round-off errors happen when you go for finite digit representation of numbers, whereas truncation error occurs when you go for truncation of a mathematical procedure. And these two are the errors that we will discuss in much more detail, and we will look to counter in our numerical analysis course. So what about truncation error? We have already mentioned that it is defined as the error caused by approximating or truncating a mathematical procedure. It is best explained through this example of a series. This is the Maclaurin series for e to the power x, and it is represented by 1 plus x square by 2 factorial plus x cubed by 3 factorial, and it goes up to infinity. So that is the representation for e to the power x. Now, if you want to evaluate e to the power x through some numerical technique, then is it possible to go up to infinity?
Sir.
Any numerical technique that needs to be ended after a finite number of steps. You cannot go up to infinity. So what will happen is that if you use only a finite number of terms, you will incorporate certain errors in the evaluation of e to the power x. This series has infinite number of terms, but when you use this series to calculate e to the power x for a given value of x, you can only use finite number of terms. Let's say we use 3 terms to approximate this series. So that means we will take the first 3 terms in this series shown here. That is the first term, second term, and the third term. So we will use only these 3 terms to get the value of e to the power x. So what happens to the rest? The rest are left out. So that part constitutes the truncation error. Starting with x cubed by 3 factorial, going up to infinity. So the truncation error here is, as you can see, e to the power x minus the 3 terms that we have considered as its approximation that has been taken on the left hand side, and this represents the truncation error that we obtain through this mathematical approximation. Now, how can we minimize this truncation error? Consider more number of terms. We have considered 3 terms in the first approximation. Let us consider 4 terms in the next approximation. So here we have plus x cubed by 3 factorial. So that is the approximation. We have 4 terms instead of 3. So from here, this is not there anymore because this has gone to the left hand side. Whatever is left over, starting with x to the power 4 divided by 4 factorial going up to infinity, that is now the truncation error. And quite obviously, this truncation error would be smaller in magnitude than the previous one when we considered 3 terms. So if you go on increasing the number of terms in this series, you will get less and less amount of truncation error. But where do we stop? If we go on increasing this number of terms, should we stop at 100? Or should we stop at 1,000 or 5,000 or 10,000? That is a very pertinent question, and it depends on the accuracy that you require. So the accuracy required for e to the power x would govern whether you are going to consider 10 terms or 100 terms. And it also is somewhat dependent on the resources that you have at your hand. If you have a supercomputer at your hand, probably it can calculate up to 10 to the power 10 number of terms in quite a few seconds. But if you have a old machine with not too much RAM in it and also an older processor, probably that many number of terms would not be possible to calculate in that computer. It will take a lot of time. So you need to consider the resources at hand as well. So this is the preliminary thing about the truncation error. But also another thing needs to be mentioned here is that I have given you an example of a series. And in lots of books, you will see that the truncation error is explained in terms of the series, because it is obviously easier to understand. But that does not mean that it is only applicable in case of a series. For example, approximate evaluation of derivative of a function, a general function, fx, can also succumb to truncation errors. It can also be associated with truncation. Let us explain that particular part of it. Now we know that f dash x is represented like this. So limit, actually this is going to be delta x tends to 0. That is my mistake. As delta x tends to 0, f of x plus delta x minus fx whole divided by delta x gives the definition, exact definition of a derivative. This is the first derivative. But this formula can also be approximated like this. So f dash x is approximately equal to f of x plus delta x minus fx whole divided by delta x, where this delta x is a very small quantity. In a numerical procedure, how do you replicate delta x tends to 0? That is not possible. What you can do is consider very small value of delta x and consider that it tends to 0. So that is the approximation. And due to that approximation, some truncation error is going to be incorporated in the approximate solution. As you can see here, truncation error is caused by choosing a finite value of delta x as opposed to the exact consideration of delta x tending to 0. In this case, how do you minimize the truncation error? Choose smaller and smaller values of delta x. If you go for smaller values of delta x, it will contain less truncation error, and the evaluated value, the approximated value, would be more closer to the exact value of f dash x. So this is the truncation error in terms of the definition of the derivative. We can also have this sort of an error in case of an integration. If we have integration fx dx going from a to b, then we know that this is classically defined as something like this. You have x here, you have f of x here. Let's say this is the curve or the function, and these are the two limits, a and b. So we consider a small strip, rectangular strip of, say, infinitely small thickness. This thickness is infinitesimally small. And then we travel that infinitely small strip of area from one end to the other to get the value of this, which is, by the way, physically the entire area under the curve in between the two intervals. Now, is it possible to get an infinitesimally small thickness? You would have to go for some small thickness, let's say h. Even if this is a very small quantity, it is a finite quantity. And as soon as you do that, you are approximating the actual mathematical procedure. And in doing so, you are admitting some truncation error into the evaluated value. In this case, how would you increase the accuracy? How would you reduce truncation error? You go for smaller h. That means number of rectangles in between these two intervals, a and b, would increase. If you approximate this area with respect to 10 rectangles, then you will have, say, large amount of truncation error. Compared to that, if you approximate this area with respect to 1,000 such small rectangles, you would get a much accurate value, less truncation. So I hope the concept of truncation error is clear to you after this discussion. Now we move on to the next error, which is known as the round-off error. Round-off error is defined as an error created due to approximate representation of numbers. The previous one, truncation error, was approximate representation of a mathematical procedure. Here, round-off error gets created when we try to represent numbers in an approximate way. Now, why do you want to represent numbers in an approximate way? Here you have to consider that the computers have finite space. They have finite memory. That memory is not infinite. So computers use finite number of digits and hence finite space to represent numbers. And that leads to the fact that computers can only represent certain numbers approximately. They cannot represent some numbers exactly. Let's consider this example. We intuitively know that 1 by 3 is equal to 0.333, and this never-ending series of 3's would occur, going up to infinity. But how do you represent such numbers in computers? In computers, you will have finite number of spaces to represent this number. So obviously, you need to truncate or cut off some part of this number to represent it in a computer. So if I cut off this series of 3's that are appearing over here after 4 places. So I am representing 1 by 3 approximately as 0.3333. You know that this is not correct because there are other 3's following this. But I have represented it approximately as this. So what is the amount of error? Obviously 1 by 3 minus 0.3333. And that is the round of error that is created due to this approximate representation. This is the value of the round of error that is present. There are also other numbers such as pi, e, √2 or √7. These sort of numbers, they cannot be represented exactly. Hence, there is need for approximation in computer calculations, and these approximations give rise to the round of error. By the way, here, remember that computers do not use the decimal system with base 10. I have given you an example of from a decimal system of base 10, but computers indeed use the binary system. So base 2 is used. So floating point number notations in binary is the way to go for computers. In general, what we can say is that any real number x, when represented on a computer, will have a floating point counterpart of it. And this floating point representation, let us say FLX, is of a form similar to that of x, but it has finite number of digits. Think of the numerical example that was just shown. So 1 by 3 is the real number. In computer, it is represented as 0.3333. So it is of the similar form, but with a finite number of digits, not infinite number of digits. And as a result, you have round of errors. Now, this floating point representation, FLX, also is known as machine number. We will talk about floating point representations and machine numbers in quite a bit of detail in the next lecture. For now, let us say that this round of error is caused invariably by representing a real number by its floating point representation. So there is a difference between the real number x and the floating point representation FLX. So the round of error is going to be FLX minus x. So this is the absolute round of error, because we are not considering the sign and considering only the magnitude of the error. So this is the round of error. Also, it can be put in a relative form. That is, the relative round of error is represented by FLX, that is the floating point representation, minus the real number divided by the real number itself. So that is the relative round of error. Now this nicely leads us to the next topic of quantification of error. Because we have just now provided some mathematical expressions of the round of error, we can now move forward and see how these errors are quantified. By the way, up to now, are there any questions?
No, sir.
No questions?
No,
So you
sir.
have understood everything up to now?
Yes,
That's
sir.
good. Okay. So let us proceed. When talking about quantification of errors, and before we start discussing about quantification of errors, let us talk about two important parameters: accuracy and precision. Errors are often characterized with regards to these two parameters, accuracy and precision. And in common parlance, common language, these two are often used in an interchangeable manner. But there is a fundamental difference between the two. So what is this fundamental difference? Let us now look at it. Accuracy is how closely a computed or measured value agrees with or approximates the true value. You have a true value or exact value on one hand. On the other hand, you have a computed result, which might be a result from a numerical solution, numerical analysis, or you may have a measured value. You have some parameter, let's say a length, you have measured it with some instrument, say vernier scale. So you can either have a computed value from a numerical analysis, which is our focus at the moment, but also this is relevant for measurements as well. So we will take both of them together. So you have an exact value on one hand and computed or measured value on the other hand. There is a gap between them. If the gap is large, then the result is less accurate. If the gap is small, the result is more accurate. So it is pretty easy to understand. How close you are to the exact value is a measure of accuracy. What about precision? How closely individual computed or measured values of the same quantity agree with each other. Here is a sense of repeatability, repetitions. There is the exact value, that is true. And on the other hand, you have several measurements or several computed values. Previously, we considered only one value. Now, here you have probably run the numerical analysis for, say, multiple times, 100 number of times. So you have 100 different results from those 100 different runs. Consider the same measurement problem, that you have measured the length with a vernier scale, but not once. You have repeated this maybe 100 times. So you have 100 number of data with you. So how these computed or measured data compare against one another, not with the exact value, how they compare against one another, that is the measure of precision. So how closely individual captured or measured values of the same quantity agree with one another. To explain this further, let us look at this figure. This is a bullseye along with certain shots at the target. If you have seen the recently concluded Olympics or Paralympic Games, you would have seen the competition of archery or even the competition of shooting, and you would have seen that such targets are present there. So what is the objective? Objective is to hit the bullseye. That means the center of these concentric circles. So that is the target. Now here on the left-hand corner, you have, say, one archer who has shot these different arrows, and they have hit at these different locations. This can be considered analogous to a number of numerical techniques which has provided you with these numerical solutions, where the actual solution, the exact value, is at the middle here. So you can see some of them have gone very close, but some of them are quite far away. So what would you say, that this process, is it accurate or is it precise? If we consider a mean of all these different, say, values, results, you will find that it would be somewhere around here, somewhere around the lower left corner. And that is quite far away from the center of the target. So this is quite inaccurate. How about the precision? You see that there is a big scatter. It is scattered over a large area. So it is imprecise as well. These individual values are not close to one another, and hence it lacks in precision. If you consider a single value, not all of these together, then this result is very accurate, whereas this one is quite inaccurate. But to get a sense of the precision, you need to consider all of them together. And if you take all of them together, you see that there is a scatter. The results are scattered over a large range, and hence this one is not precise enough. Along with these two terms, accuracy and precision, we can also define inaccuracy or bias. So it's a measure of systemic deviation from the true or the exact value. As I said, if you consider the mean of these scattered results, it would be somewhere around the left-hand side of this target and quite far away from it. So this one would be inaccurate. It would be biased towards the left-hand side. Similarly, imprecision, also known as uncertainty, refers to the magnitude of the scatter. It measures scatter of individual computations or measurements of the same true value. Now, what about the figure just on the right of it? This, let's say this is the first figure. This is the second figure. Here also you see that there is a substantial scatter of the individual results. So it is not precise. But what can we say about its inaccuracy or bias? Is it too biased or too inaccurate? You will see that all these points, all these results or measurements are centered around the actual value or the exact value. So you can say that this result, this group of results, is more accurate than the previous one. So along this axis, there is increase in accuracy. Now let us talk about the third figure. Third figure being this one. Very small scatter as compared to the previous two cases. So this is much more precise, but it is not accurate. Why is it not accurate? You can see that these results are grouped quite far away from the center of the target, which is the exact value. So according to the definition, how closely a computed or measured value agrees with the true value, it fails according to that definition. None of these actually closely match with the exact value. And if you consider the mean of these results also, it will probably come out to be around the same place as the case 1. So it will be somewhere around here, lower left. So this is also inaccurate. Inaccurate but precise. Now let us come to the final figure. That is the fourth figure. Here you see that they are tightly grouped and around the exact value. So quite obviously this case is more precise than the previous one and more accurate than the previous ones. So to this direction, towards the right, you have increasing accuracy, and upward you have increasing precision. We want numerical methods which are both accurate and precise. So this is the intended objective. That sort of a grouping, that sort of a result is our intended outcome. Now let us look at another example, just to crystallize the idea about accuracy and precision. Here we have on the x-axis certain measurements. These are indicative of measurements or individual runs of a numerical method. And each of these would give us a solution, numerical solution, or a measured value that is represented on the y-axis. What is the exact value or true value? This horizontal line represents the true value. So what would you say that this process, is it accurate? Is it precise?
Not precise, sir. And not
It is definitely not precise. But accuracy, you have to talk about the individual runs, isn't it? Because it does not have to do with the group. This particular solution comes quite close to the true value. So this one is quite accurate. But this one, this result, or this result, they are quite far away from the true value. So those are inaccurate runs of the numerical solution. Overall, we can say that the previous figure, the first figure, is imprecise, but to some extent accurate. Certain runs of it are accurate. What about the second figure?
It is precise.
It is precise, but consistently away from the true value. So this one corresponds to an inaccurate but precise method. Your results are repeatable. There is repeatability. They come along probably the same line. You draw a best fit curve through them, they will go probably through this somewhere below the true value. And the gap between the two would, this is probably the best fit line approximately. And this gap is indicative of the error. For our present course, when we consider numerical errors or errors in general, this is going to be a collective term. That means it is going to represent both inaccuracy and imprecision of the numerical predictions. So both will be clubbed together under this term error. We will not separately calculate the inaccuracy and the imprecision. Both will be considered under error. But it is imperative that the numerical methods should be sufficiently unbiased or accurate, as well as precise enough to meet the requirements of a particular engineering problem or a design problem. So that is the main thing about considering errors. Now we come to certain definitions regarding different types of errors. These are different parameters that we look to define when quantifying errors. First of all, we'll look at true error. What is true error? This is the discrepancy between the true or exact value and the approximate value. So the expression for true error, represented by capital E subscript T, is true value minus the approximate value. Not difficult to understand. In fact, very straightforward. What is true error? But still, let us consider one example. One problem that will probably clarify the concept of true errors in our mind. In this example, we are considering the derivative of a function at a particular value of x. As already mentioned in a few slides before now, f dashed x, that is the derivative, first derivative, can be approximated by f of x plus h minus fx divided by h. Here, that delta x term I have replaced with h. Now, the problem that we are considering is that we have to evaluate f dash 2 with a given value of h of 0.3. And what is fx? Fx is an exponential function, 7 e to the power 0.5x. Now, this is a very simple function. So, we can analytically solve and find out the exact value of f dash 2. This is known to us from our knowledge of differential calculus. So, f dash x would be 7 into 0.5 into e to the power 0.5x. We are already given the value of x, where f dash x needs to be found out. We put x equal to 2 and get a value of f dash 2 as 9.5146. This is the exact value because we have solved it analytically. There is no errors in this particular calculation. But now let us go for the approximate answer. So as I said, this is the true value and this is the approximated value. So we know x and h. We'll put them in their appropriate places. And after the calculations are over, we find out that f dash 2 is given by 10.265. That is the approximate value. Right? Clearly, there is a difference between them. And that difference gives us the true error. A true error of minus 0.751. Here we are only interested in the magnitude of the error rather than its sign. So, quite often, errors are defined as absolute values. So, what you will find is that if x dashed or say x star is an approximation to the exact or true value x, then the absolute true error, previously we had defined true error, now we define absolute true error. And this absolute true error is given by magnitude of x minus x star. Now, what is the disadvantage of considering this absolute true error? It takes no account of the order of magnitude of the value under examination. If you consider true error or absolute true error, then order of magnitude is not taken into account. What do we mean by this? Consider this example. An error of a centimeter is much more significant if the length of a shaft is being measured rather than the height of a building. What do we mean by that? Suppose you have a 10 centimeter long shaft. It is to be assembled with other components in a critical machine. So if that shaft length changes by 1 centimeter, it might cause big problems in assembly. It might not fit into where it was supposed to be assembled. Think of a crankshaft of an IC engine. If its length is changed by say 1 centimeter, probably it would not assemble with the other components inside the engine, and it would cause certain problems. However, if the amount of error is 1 centimeter, in case of the height of a column or height of a building, that does not create any sort of problems. So the context is important. Also, another example that is appropriate here that deals with the order of magnitude of errors is the case of stress and strain. You have already studied about stress and strain in your previous semesters, probably in strength of materials. Usually in SI units, stress would have a value of around of the order of 10 to the power 6. Whereas strains would be of the order of 10 to the power minus 3, 10 to the power minus 4, even less than that. So in case of stress, deviation of 1 unit is not that much. Instead of 700 MPa, you probably consider 701 MPa. That error will not be too much. But the true error is still 1. In case of strains, if you have a true error equal to 1 unit, where the order of magnitude of the actual values, strain values are 10 to the power minus 3 or 10 to the power minus 4, then that is a huge error. And that is the problem with true errors, that it does not take into account the order of magnitude of the value under consideration. How can we rectify that? There is a way to account for the magnitude of the quantities being evaluated or measured, and that is to normalize the error with respect to the true value. And in that process, we obtain a relative error. How do we define a relative true error? This is simply the ratio of true error and the true value, the exact value. So if you simplify it, this is on the numerator true value minus the approximate value, that is true error, divided by the true value itself. And that gives you a relative true error. This can be expressed as x minus x star divided by x. Obviously, here we consider only the magnitude or absolute value of the relative error. So we get absolute relative true error and represented by epsilon t. Let's consider this example. It's quite similar to the previous one. And here we want to calculate the relative error for the same value, that is f dash 2 with h equal to 0.3, where the approximate first derivative is given by this function fx. So approximate value we had already calculated in the previous slide. True value we have already calculated in the previous slide. So these are taken directly from there. So what was the true error? The true error also we had calculated previously. This was minus 0.751. So now we calculate the relative true error. The relative true error would be this true error divided by the true value. And that is what we have done here. And we have obtained a value of minus 0.078936. This is the relative true error. We can obviously convert it to percentage, multiply it by 100 and consider only the magnitude, and we get 7.8936% relative true error. But here we need to consider one thing. We have the true or exact value in these definitions. But exact values or true values are only available for certain situations, often for simple cases. And these exact values are obtained as a result of certain analytical solutions. Now, numerical techniques are geared towards providing answers of complicated problems. For one thing, just have a think that if you already know the true value, if you already know the exact answer, why would you need to go for an approximate technique? That becomes redundant then. So for the simple situations, numerical analysis is not that important because you can solve those simple cases analytically and obtain the exact results. Numerical analysis takes up more importance when analytical techniques fail, when these techniques cannot provide us with exact solutions. Now, we do not know the exact solution. So what do we put in these definitions? If you do not know the true value or the exact value, then how do you calculate true error or even relative true error? That is not possible. So in that case, what we do is, and quite obviously, these are the real life complex situations where the true or exact value is not known a priori. That means not known beforehand. So in those situations, we have to think about something called an approximate error. In absence of knowledge of the true value, one has to use some approximate value as the best estimate of the correct or exact or true value. And in such cases, the error is known as the approximate error. So just to recapitulate, in complex situations, we do not know the true value or exact value. So we cannot calculate true error or relative true error. What is the alternative available to us? We have to approximate. we have to approximate the true value itself. So we take a best guess or best estimate. And the error in this case, considering that approximated value gives rise to approximate. We define it as this. So approximate error is equal to approximated true value minus the computed value. Sometimes this will be also written as the measured value. But as we are in the domain of numerical analysis, we are talking about numerical computations, we will take it as a computed value. One more thing to consider here is the case of iterative numerical methods. Numerical methods where the process is repeated a few number of times to arrive at a correct result. Not a correct result, an acceptable guess, an approximate solution. So how do we define iterative numerical methods? These are numerical methods where the solution is approached with increasing iterations. You go on increasing the number of iterations, and in that way you approach a correct or exact solution. You will probably not ever achieve that exact solution, but you can go pretty close. So in those sort of situations, that is in case of iterative numerical methods, approximate errors are defined as current approximated value minus the previous approximate value. There are, of course, number of iterations. Probably the iterative procedure would run for maybe 10 times, for example. So the same numerical calculations would be carried out in a loop for 10 number of times. And in each of these iterations, we'll look to minimize the error. So obviously, you need to calculate the approximate error at the end of each iteration. How do you calculate the approximate error? The current approximated value minus the previous approximate. So at the end of the 7th iteration, what would be your approximate error? The approximate value calculated at the 7th iteration minus the approximate value calculated at the 6th iteration. Subtraction of these two approximate values would give you the approximate error. And in case of approximate errors also, it can be normalized and expressed as relative error, obviously to account for the magnitude of the evaluated quantities. How would you write that relative approximate error? That is the expression. So x minus x star divided by x. And here we have considered absolute values as well. So here x and x star are as follows. So x is the approximation to exact or true value in case of estimated true value, or it is the current approximation value in case we are considering a numerical procedure. Whereas the x star is the current or computed, calculated approximation. So that is all about the relative approximate error. We consider this example next. This is the same example again. We have this value here, that is the approximation to f dashed x. The function is same as before, 7 e to the power 0.5x, we are trying to calculate this f dashed value, the first derivative, at x equal to 2. But here we have two different values of h. So h is equal to 0.3 in the first case. In the second case, h is equal to 0.15. So let us consider this as part of a numerical procedure where in each step we are reducing the step size. Step size here is indicated by h. So at the first iteration, we have h equal to 0.3. In the second iteration, we have halved it. So if we have a third iteration, then it will be half of 0.15, and that would be 0.075. But anyway, let us proceed with this example. The first part of it is known, that we have already calculated f dash 2 at h equal to 0.3. The value that comes out is 10.265. The next is the part B, where we repeat the procedure. Whatever we have done over here, exactly that is done again. But only thing different is the value of h. Previously it was 0.3. Now we are considering it as 0.15. As a result, we have obtained a different value for f dash 2. Is 9.879. By reducing the step size, we have in fact approached the exact solution. Remember that truncation error reduces as we go on, reducing the value of delta x or h here. So that is what has happened exactly. We have reduced the error from the previous step. But now if you want to calculate the approximate error, then we do this: present approximation minus the previous approximation. Both the values are available, and we get a value of negative 0.3851. What would be the relative approximate error? That can also be approximate error divided by the present approximation. We can take a percentage of it also. If we now go ahead and calculate the same thing with h is equal to 0.075, that is half of 0.15. Follow the same process, we will obtain a value of f dash 2 at, let's say, h3. This was 0.075. So we'll put those values here, that means here, and we'll calculate the value for f dash 2. And that is f dash 2 at h3. So this is the current approximation now. What is the previous approximation? Previous approximation now becomes this value. We do not consider this one anymore. We'll take this one. So the approximate error would be calculated by subtracting this previous approximation from the current approximation. And then you can go ahead and calculate the relative approximate error as well. So that ends the discussion regarding quantification of error. If you have any questions, please go ahead. No questions at all? you hear me?
Yes, sir.
Yes, sir.
Okay. So sometimes the connection gets lost. So if you are not responding, I'm getting confused that whether I have it with you or not. Anyway, just a simple.
I have understood clearly, sir.
Okay. No, but one thing is that sometimes we have power issues and I may lose the Wi-Fi connection. Okay. This is not just for today's class, for future classes as well. So if I am at the presentation screen, I do not have any indication whether the call has dropped out or I have left the Google Meet. So in that case, what you should do is one of you just call me up. If you see that I have left the meeting and the presentation has stopped, then you just call me up on my phone and let me know that that has happened. Otherwise, what will happen is that I will stay at the presentation screen and have no idea that you are not there. So I'll continue with the lecture and it will not be recorded and it's just a futile effort. Anyway, just general information that if you just see sometimes that I have left the meeting suddenly, probably due to power outages or Wi-Fi failure, let me know. You can send a text also. I have the phone with me during the class, so I'll get to know immediately. Anyway, let us now concentrate on the final part. We are almost at the end. And the final part of this presentation is minimization of error. How do you reduce errors that you obtain in a numerical procedure? This is done in terms of a pre-specified error limit, which is also known as tolerance. Let us take into consideration the numerical procedure that we discussed in the last example. So it was a repetitive numerical method, iterative numerical method. In that, the relative approximate error can be computed at the end of each iteration. Just to clarify, if we talk about the previous example, we had h equal to 0.3 at the beginning. Let's say this is iteration 1. Let's say, sorry. This is I1. And we get some epsilon A magnitude at the end of this. Next, we have 0.15. This is iteration 2. And we get some epsilon A at the end as well. Next, we have 0.075. That is iteration 3. And again, we calculate an approximate error. So like this, you can continue. And at the end of each stage, each iteration, you will have an approximate error like this. In the best case possible, best case scenario, you will see that as you are decreasing the value of the interval h, this will keep decreasing as well. That is what we want, decrease in error. So the absolute value of epsilon A needs to be compared against a minimum acceptable tolerance which was previously specified by the user. And that is dependent on the requirement. This is called the pre-specified tolerance epsilon s. So we have an epsilon s as well. And at each step, we compare this epsilon s against epsilon a. If this absolute approximate error becomes less than or equal to this specified tolerance, then we say that the acceptable error limit is reached. Remember that we had at the beginning posed a question that how large error is considered as a large error, or how small an error needs to be in order to be considered as a small error. So this is the answer. We specify an error limit, also called tolerance, and then at the end of each iteration, we compare the evaluated approximate error against that pre-specified limit. As soon as that approximate error, relative approximate error, falls below or becomes equal to that pre-specified limit, we say that acceptable error limit is obtained and no further iterations are necessary. So this acts as a termination criteria. That is how you terminate the iterative numerical method. To take this forward just a little bit, suppose at h equal to 0.0375, you obtain an epsilon A which is less than this pre-specified error limit. At that stage, you will stop the iterations. You will not reduce h any further. So this is the expression through which we control the amount of error in the iterative numerical method. And this is going to be quite important in our course, and we will use it quite a few times in future. That, as I said, is known as the termination criteria, and the result is assumed to be within prescribed acceptable level once this termination criteria is reached. It simply indicates that the error is minimized to a satisfactory level. So that is how we reduce continuously the errors and errors involved in the each iterations, and finally how we terminate the process. Now the next question that would arise is that we have to specify epsilon s. So how do we know what should be the exact value for this epsilon s? The answer depends on how much accuracy you want in your result. Hypothetically, just consider a numerical solution where you want the result to be accurate up to 3 decimal places. That means after the decimal point, you are accurate up to 3 places. If you want the accuracy to go up to 5 decimal places, that means after the decimal, 5 places would be accurate. Do you think that they would be requiring the same epsilon s or different epsilon s? So that, I think, points to the idea how you can set your pre-specified error limit. The more accuracy you want, the less would be the value of pre-specified error limit or tolerance. And that nicely brings us to the concept of significant digits. Because it is convenient to relate errors to the number of significant digits in the approximation. That is basically number of digits probably after the decimal places. There is another way of saying it. Now it can be shown that if the following criteria, the given expression is satisfied, that is this expression, if this is satisfied, then at least n significant digits in the approximate result is correct. So if you want n equal to 3, then you put 3 over here, calculate the value of epsilon s, and then compare it against the relative approximate error. Conversely, if you want n equal to 5, then you put this one here and calculate a separate epsilon s, which then would be compared to this epsilon a. So this is a very important expression. Derivation of this is not at the moment important for us, so I'll skip that. But you do need to remember the expression, how to calculate the epsilon s value. It is dependent on the number of significant digits. So that now raises the question, what is a significant digit? The answer is very simple. This is the number which can be used with confidence. So significant digits or significant figures of a number are those that can be used with confidence. Probably this idea is not clear from this definition. So let's take this example. We have two numbers here. Same numbers, but represented differently. First one is 18.7. The next one is 18.70. What is the difference between the two? Can you just tell me what difference there is between these two representations? Okay, the answer is written directly below it. So if you read that, you will probably come to know that 18.7 signifies that we are only confident about the first decimal place. That is the first place after the decimal point. That much we are confident about. We do not know anything about the numbers that would come after that. So that is why it is written as 18.7. Here one is confident only up to the first decimal place of the decimal point, and there is no confidence about the next digit. Whereas 18.70 signifies that we are certain that the number that follows 7 is 0. It signifies a certainty that the digit after 18.7 is indeed 0. We can consider this example. Let's say we have a speedometer. We have 40 here, we have 50 here, and there would be 10 divisions from here. Let's try 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Not equal divisions, but anyway, that would do. So each of these marks represents one number. This is 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, and 50. Suppose the indicator is somewhere around here. So what would you say that the speed is at the moment? Any answers? This is 48.
48.
This is 47. By the way, this is not exactly 48. It is just before 48. Isn't it? So why didn't you say 47.9 or 47.8? Because you cannot say that with confidence. It is more than 47. It is less than 48. That we can see. But it is very close to 48. So we are confidently saying that it is 48. If it was right at the middle of 47 and 48, then you could have said that this is 47.5. So usually what is done is we say something which we can know or say with confidence. So here, significant digits would be those numbers that you can use, that you can say with confidence. And in general, this is not difficult. You are just required to count. So ascertaining the number of significant digits or in a number, in a representation of a number, is not that difficult. But it might be complicated in some cases if leading zeros or trailing zeros are involved. For example, these numbers over here. How many significant digits are there? They all have varying number of leading zeros. Now, these leading zeros are not always significant because they are probably necessary just to locate the decimal point. So you will be probably interested to know that all of these three representations, they have 4 significant digits. These leading zeros do not matter. They are present there only to place the decimal point at the appropriate location. Same happens for the trailing zeros as well. In case of large numbers, it may not be clear how many, if any, of the zeros are significant. If you have 1, 2, 3, 00, you may have 3, 4, or 5 significant digits, depending on whether the zeros are known with confidence or not. So how can we remove such confusion? You may take help or take resort to the scientific notation. To remove such confusions, we can represent 1.875 into 10 to the power e, where e is -3, -4, -5, depending on whether you want to represent this one, or this one. And now it is quite clear that we have only 4 significant digits. Similarly, 12,300 could be represented as 1.23 into 10 to the power e, where e is equal to 2, 3, or 4, depending on what you know with confidence. How many zeros you know with confidence. So that is all about significant digits. Significant digits are usually important in order to decide what would be the pre-specified tolerance, pre-specified error limit. If you have 5 significant digits, you have epsilon s as some value. But if you have 7 significant digits, then epsilon s would change. And that would be calculated. The value of epsilon s would be calculated from the expression given here. Once you have calculated that value, then you can compare it against the relative approximate error and minimize the error in such a way that you get an acceptable solution. So that brings us to the end of the class or end of the discussion regarding errors. Thank you for your attention.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Any questions?
Thank you, sir.
Hello, sir.
Thank you, sir.
So you told me to remind me of the attendance.
Yeah, sure. I'll give the attendance. Your roll number is
38.
48. Anonna. Okay. Anybody else who is present here? Marked as absent? Joydeep?
Sahaja said.
Yeah, you are present. If nothing is mentioned in this column, you are considered as present. Only those who are absent, I have marked. Okay.
Okay, sir.
Okay. So you do not have any questions from errors. That is quite an encouraging sign. But what I have found from my previous experiences is that there are no questions in two situations. Either you have understood everything or you have not understood anything. So I hope this is the first case, absolutely the first case, and you have understood the topic. And if you have any questions later on, then of course you are free to consult with me. You can send or text me, WhatsApp or mail, or you can put your questions in the classroom. You are all able to access the classroom, I hope.
Yes, sir.
Yes, sir.
Yes, sir.
Okay. So again, I will circulate the recording of this class as soon as possible. I'll also give you some links to the problem that I discussed in the beginning of the class. That is for Android phones that crashing the phones with that wallpaper. You can also read about that problem in much more detail in the internet, or you can see certain YouTube videos are there.
শেয়ার করে দেবেন
So, yes,
স্যার পিপিটিস গুলো একটু শেয়ার করে দেবেন
PPTs I have already shared the previous PPT. I think the previous class presentation you have got.
ইয়েস স্যার
Okay, so no problems with that. For each class, the presentation or even the annotated class note means whatever I have done on the PPT, whatever I have scribbled over there, that also I will make a PDF and I will circulate. Okay, it will be uploaded in the classroom. So that is all for today's class. Next, I will meet you tomorrow, right?
Sir.
Probably
Yes.
last week there was some confusion regarding whether the class is from 2:30 or 3 o'clock. Some of you may have joined late, but the last week case was different because I had a meeting from 3:30, so I had to start the class earlier. So tomorrow, hopefully, the class will be from 3 o'clock. But do take notice of the mail that I sent with the link. So the time will be mentioned there, and according to that, you can join.